Hi, everyone, and welcome to the first mini workshop of WhaleTeq. I am Stefan. Thanks for joining us today. We are going to talk about something all medical device engineer knows intimately, and probably a love-hate relationship with ECG compliance testing. Specifically, we want to look at how can we stop doing things the hard way and stop using automated solution to make our life easier. Here is our game plan for the next 15 minutes, and we will all know the IEC standard 60601-225, 2747 is the Bible for ambulatory diagnostic and monitoring ECG categories. But let's be honest, following manually is painful. So I'm going to walk you through the three things: the hardware challenges, how to teach breadboard, the software advantage, visualizing your pass-fail criteria, and the results, and automation feature using our SDK to let your tester machine do the work. Please feel free to ask questions anytime using the chat function. We will have a dedicated QA session at the end to address as many of them as possible. Also, due to the limited QA time, unanswered question will be answered and compiled in a PDF file and shared with every one of you over mail after the live session. I guess we're all set, and let's dive right in. First, meet the team. We call these the global trios. On the left, we have an MEC 2.0 for 12-lead ECG database playback. In the middle, the SECG 5.0 AIO. This is your premium performance testers. And on the right, the CMR 3.0 Plus for noise rejection test. Also, your trouble rejector. We will review how they dedicate to compliance tests in a few slides. I know many of you look at compliance as the checkbox, a hurdle you have to jump over to get your Class 2 medical device approved. But at WhaleTeq, we believe the advanced ECG development actually starts with compliance. If you look at the left side of the slide, you will see the full list of test items from the IEC's. It's also 01-2-25, it looks intimidating, right? But whatever you are working on the 25, 27, 47 standard, well, actually, we can simplify the entire map. We have distilled all the compliance costs into 6 essentials. And let's break it down. The first is the essential is algorithm performance. This is where you can verify your algorithm brain, the standard as all the ECG developer to test the accuracy of the amplitude and time domain measurements. We do this by comparing your device measurement result against reference value, which are essential, and the global answer found in the CTS and CSE database. This ensures your algorithm is interpreting cardiac signal correctly. And then the rest of the essential goes to the electrical performance. And there are 5. And we move away the clinical database. And here we are using a basic function waveform, okay? Like sine, square, and triangular. Let's walk through why each of these 5 capability is crucial for your hardware design. First, amplitude accuracy. This is fundamental. We test this to ensure your device can accurately replicate the patient signal in digital record. We need to know that your hardware catch everything from the tiny peak wave to a large R wave, even pacemaker signal without distortion. And dynamic range, human ain't perfect, and electro aren't always perfect either. We test dynamic range to ensure your ECG machine is compatible with a wide variety of patient group, and your hardware must be able to handle unexpected DC offset or gap that naturally occur between different limbs. And input impedance, this is define your system's sensitivities. And we test this to verify the ECG machine represent a sufficient load. We need to ensure it can couple the weak physiological signal from the patient to your analog front end, and as completely as possible. Frequency response, think of our all ECG machine as a specific type of a bandpass filter. We test this to confirm that your low pass and high pass cutoff frequency match your design definitions. Typically, we are verifying a signal between 0.67 Hz to 40 Hz pass-through with maximum amplitude loss over 30%. The last is noise rejection. The real world is noisy, and this essential tests the hardware ability to reject internal noise generated in your ECG circuit, also the external mains power noise. So those are the 6 pillars we need to take care of. One of them is your algorithm, and 5 for your electrical hardware. Now the question is, how do we test all these efficiently? And let's move to a solution. And we believe in using right tool for the right job. And this is why we developed the global trio. Our 3 specialized instruments, it cover all full compliance spectrum. First, top left is the algorithm testing. We have the MEC 2.0. Its job is to verify your entire system from analog input to digital output. It takes clinical ECG database and convert the digital file into a precise analog signal and play right into your device leads. And it is critical to testing your full signal chain, not just the software parts. And second, left down for the electrical performances. And this is the core testing area, and this is handled by the SED 5.0 and the CMR 3.0 plus. And this is where the real-time saving begin. In the past, when you test things like input impedance and CMR, you had to manually build this test circuit required by the standard. You need to find the external components, breadboard, and lots of the manual verification, and calibrate and maintain the circuit every single year. And we have completely eliminated this kind of hustles. Both 5.0 and 3.0 plus model have the required compliant test circuit embedded and integrated into the hardware. All those switch, resistor, capacitor inside the boxes controlled by the very friendly software interfaces. So simply put, SE 5.0 AIO, it means that you can run all these tests in blue words by clicking buttons. And for CMR 3.0, its specialization is even more critical, actually. We dedicate these guys to entire noise rejection. We design internal shielding, let you achieve those high minus 120 dB rejection ratio right on your desk. So without needing to like a full-fledged and shield chamber. And those devices ain't just signal generator or like a test fixture. It's an integrated compliance analyzer, making the hard part of the standard easy. Now, let's talk about the algorithm. You need to prove your accuracy using database like CTS and CSE. Usually, it means that you just play the digital file right into your algorithm, so the digital file becomes raw data, and it has a test value. But that means the analog front end, which is the cable connector and the raw signal processing hardware over here. And that might bring extra loading. In the real world, we call it signal distortion. So certain compensation logic need to be there to justify the measurement error. So we propose MEC 2.0. It takes digital database, convert it into the precise analog signal, and feed to your analog front end. And this is a way to verify your whole signal chain. And however, the real nightmare starts when you start comparing your test value and the reference value in the standard. And there are thousands, and they outnumber us. But here is a game changer. Please look at the colorful table. This is our CDCA, Compliant Database Comparison Analyzer. After exporting a test value to a specific format from your ECG software and load it into the CDCA. CDCA does the heavy lifting for you. Green cells means you pass. Pink cell, you fail. Yellow cells excluded based on the standard. It automatically calculates the difference between your test value and reference value. You don't need to open Excel sheets, and you can just see the health of the algorithm in 5 seconds of analysis. And this is a strong finisher for algorithm testings. Regarding the electrical performance, look at the first test circuit diagram from the standard general test circuits. In all day, you need a 620K ohm 51K and 2 pieces of a 4.7 nanofarad capacitor and a DC offset source. And you have to wire it out and check connection, pray any wire doesn't come loose. With SE 5.0, we put everything in a box. And look at the software interface on the slide. See those colorful boxes? Whatever the circuit has, our software offers a setting to control it. Now, let's see how convenient it gets from some example. On the left, is a class of input impedance from the standard. At the top right is a GUI of SE 5.0. You can set up the simulation parameter based on how you interpret from the class. At the right bottom corner, it presents the backend or ECG display, which shows real-time ECG trace and measure the sinusoidal amplitude. From there, you can measure the difference amplitude when the 620K ohm resistor and 4.0 nanofarad capacitor are included or excluded, while overlay with plus minus 300 millivolt DC offset. So this is the measurement without it, and this is the measurement with those capacitor, resistor, also the offset. And you get to calculate it using the easy voltage divider calculation, and then you can reverse to find out your actual input impedance. Now, even better, SE 5.0 offer like an optional standard assistant. First, enable all the test combination, so you can just run tests by one touch, and then get into this execution window and observe on the amplitude and waveform on your backend or ECG display, and then you enter what you find there. And when our table get the value, we can automatically judge based on the criteria stated in the standard. And any value that's considered fail will turn red in the table. Another example we have today is the linearity and dynamic range. On the left is the class from the 25 standard. Purpose is to limit the amplitude change detected by the ECG and must be in plus minus 5%. And giving the condition detail in the method, a method shows the step to give a 40 Hz sine wave overlay with stronger 2 Hz square wave, while overlaying with extra plus or minus 300 millivolt DC offset. And results follow the purpose to verify the amplitude measure by the ECG machine. So if you are familiar with the standard and interpret it properly, and then you can just operate a GUI and check the ECG trace on your backend or displayed. Well, since we go this far, why don't we just streamline it? Once again, standardization software. First, we can enable it, so there are only 6 combinations you need to test, and then run by a touch, and then you observe on your back end and get the reading and enter to the table. So when table get the reading, we will compare it with the criteria and we will make a judge. Fail turns red. So likewise, you can use this to run the other test classes in such a very efficient manner. In addition, for most of the test classes, SE 5.0 enable wider test range in case you are pushing the limits of your ECG hardware. Now, let's look at the second test circuit from the standard, the one for CMRR. But let's take a pause to notice an interesting fact. Unlike the previous test circuit to produce a functional wave or physiological wave, CMR test circuit produce mass power noise instead. It's to see if ECG machine suppress the noise with a proper hardware design. And just so you know, the application behind the scene in the real world is that in this illustration, the brown noise is the mains power noise. And it pollutes both inputs of the ECG amplified, so the noise getting to the leads. However, with a proper hardware design, the noise wears away in no time. So back to the testing, the required resistor and capacitor and the switch or relay or there, CMR 3.0 plus got it, and we integrate it and we offer the setting for you to control it. And the test method is to give both inputs of ECG amplified, so every output leads will be given with the same signal, and the signal is actually simulating the mains power noises. So when every lead give it the same signal, and that is the balance conditions. And we're asking the CMR ratio is gonna be minus 89 dB according to dash 225 standard. And later in imbalance conditions, closing the switch 1 to add 51K ohm on one electrode of a lead, and then still ask for the same rejection ratio of the mains power noise. Again, minus 89 dB. So we can use a LCD panel and a CMR 3.0 GUI to set a condition at a time, but since the amount of the testing is quite a lot, given the amount of the ECG lead. So that let us feel the power of the standard assistant software again. So there are the clear procedure to follow an easy understanding auto setting for you. So on the back end ECG display, we expect a flat line under the balance test conditions. Normally is way higher than minus 98 dB. And in this case, it achieved minus 120. However, in the imbalance condition, there will be a noise sneaking through the ECG amplifier and showing on the lead. And through a calculation, you usually drop about 20 dB. Okay, I think we covered the hardware and software, but what if we want to run all these tests while you are sleeping? This is where SDK of WhaleTeq come in. We provide a software development kit that is free of charge, downloadable on our website, helping ramp up the throughputs for developers. User-friendly, all the API are well documented and Python code are given. And it also compatible across platforms like Windows, Linux, and Raspberry Pi. You can write a script that controls ECG and CMR unit to run full ECG compliance sequence automatically. Then I took 601-2.27 for example. And this is perfect for regression tests across different builds or end-of-line testing on the factory floor. Almost 5 years back, we had a client integrating other, which is older ECG, SECG model, we call it SECG 4.0, and CMR 3.0 plus to the automated production text feature. And that's in their factory. And the framework can be easily understood like the centralized computer use the WhaleTeq API to control SECG model and CMR run all the kind of sequence tests and let the signal go through their front end, generate raw data, and then the algorithm will come out the measurement also displayed. And then their centralized computer, once again, use their own API to log those data back to them. And finally, the computer judge pass-fail as configured, and these complete the auto test flow. And we also share this generous testimonial on our YouTube, where our one test software controls CMR and SECG in turn. And one important takeaway we learned from this customer is that saving time is actually minor because the test itself cannot be shrunk due to the strict guidance of the standard. But what was greatly spared is the training cost for the operator who run the test on the factory floor. So originally, the manual production testing was the job for 5 to 6 skilled technicians, and each of them required 2 to 3 months of training. And since they set up the automation, they spent less than a month to get new technicians familiar with the production testing, and maximum 2 people can undertake the job. So to wrap things up, let's summarize the WhaleTeq way. Integrated circuits. We embedded the compliance circuit into the SE 5.0 and through CMR 3.0 plus, no more breadboard. And analog databases. MECG 2.0 allow you to test your full system with a real-world analog signal. Compliance Assistant, our software streamlined the test flow. Full automation, the SDK lets you automate the entire process for regression testing or manufacturing. If you're tired of manual calculation and messy wiring, I invite you to try our solutions. You can download the SDK right away now from our website to see how easy it gets. I'm Stefan for WhaleTeq's. Thank you so much for your time. I'm happy to take your answer and all your questions. So let's see what we can have. All right. So see, as you are typing your questions, we have an audience. Okay, good. Hey, Vignesh, is there an example for automating tests and results? Yes, the example is exactly what I mentioned at the end. Okay, the customer empower their production line using our SDK, SE 4.0 and 3R 0 plus, right? So you might want to specify the example you want to know. So normally when we talk about when a customer asks for example or some sample codes, we have the Python sample codes where we help you get hands-on. So there is a C header file that will make clear all the definition and the functionalities. But there is a Python sample codes that actually practice the API. So I know in a production line you might use a C#, but that's no problem. So first things, you need to write the wrapper. So we give you Python, but we also offer a PyWrapper. And for your C# auto test software, you might need to create a C# wrapper, and then you create other functions, and that can refer and call the functions from the wrappers. So that's basically how it works. And if you want to talk something or consult something specifically, we can take this offline. Thank you, Vignesh. What's the minimum microvolt we can generate? What are the sensitivity and resolution? Is there any way to simulate movement artifact? So the specification of our SE 5.0, it's 1%, okay, above the microvolts. So so minimum we can give is 0.5 millivolts, but the accuracy below that, it might be a lot, it might be 5%, but anything above the 0.5 millivolt, it's 1%, right? And for the simulate movement, we have a function for that. There is, right, let's get, yeah. So for Nino, we can simulate movement by getting to this, this is our SE 5.0 GUI and special function. You can go to NSD noise, and there is a motion artifact in this database. So we can superimpose this motion noise onto any signal here. Yeah, hope I answered your question. before 5 is 12 times as a time to the noise. See more testings. Yeah, let me zoom you zoom well. Okay, cool. Standard is times more. Okay, to Nazi's input impedance is in ohm, and CMR testing is a ratio and measured in the dB. So you mean 12 times more sensitive? We might want to, know more what it means. Yeah. Okay, no worries, and you can write us something more, and we can answer you and compile it in a PDF file. Because right now I can't connect the resistant units and the ratio, which it has no units, and I don't know. I can't understand for now the 12 times. Can you simulate both power line noise and baseline wandering noise at the same time? The answer is, yeah, to Ahmed is no. So power line noise, yeah, wait. So over here, the baseline wander is here. And the answer is not from our GUI, but you can make such a raw data. So for example, you have a power line noise, and that is a data stream, and you have a baseline wandering noise, that's another data stream. So there's data stream 1, data stream 2, and then that's come the data stream 3, which is your real ECG data, and you can synthesize the 3 data stream into a file and then turn into the WhaleTeq's format, and then you can go to the file replay, and we can replay such a signal. So our GUI doesn't offer to add power noise and baseline wander at the same time, but you can create such things externally and import for us to replay. Thank you, Ahmed. And which type of test class can be done? Which type? Oh, it's the, so, hey, thank you, Yuanfang. And the type of the test classes is what I meant in the very first. So let me go back real quick to the slide at right here. Yeah. So this is how our global Thank you. All right. So Nazi, I will encourage you to write us offline so I can get back to you. I think that's a very meaningful questions, and the answer will be very beneficial to everyone, to every audience. Hi, Robert. Can we simulate ECG SpO2 simultaneously? I mean, both ECG signal and SpO2 are coming from the same person. The answer is yes. Okay, answer is yes. So once again, let's look at the, so you are talking about the same person. So there will be 2 answers. First is we are using our signal, our simulate signal. So in the PWTT mode, we can simulate ECG and PPG, and they are all simulate signal. You can send from our ECG electrode of SE 5.0 and also reflectant or transmittant probe module. So we can give you electrical signal and optical signal at the same time, but they're all simulation, not real. But if you're looking from the same person, because I noticed that's why you are writing, so you can load such things. So once you plug in the PPG module, no matter reflectance or transmittant, there'll be another blank for you to fill in the data. All right, actually here. Low raw data. over here. So you can load in. So they are, rad PPG, infrared PPG, and the ECG. So that after we load, and we will release the ECG and the PPG, real patient data back to your front end. All right. Oh yeah. Oh, thank you. Hi, Emmanuel. Hey, what's the target group of this testing machine? Target groups. I think target, it means that who might want to use it. So we have a very strong, user base. They are the certified test lab. And those certified test lab, they verify all the ECG applicants, all the manufacturers, they submit their device for verification, and then those lab, they will run the test on their ECG prototype and then they will give them the stamp of certifications. So they adapt a lot of WhaleTeq's instruments actually, and because those lab use it, all the manufacturers want to make sure they pass, because there's going to be a fee to have the lab to verify their device. So that's why all the manufacturers also prefer to adopt the same model of instrument. So the two big and strong user base are the certified test lab as well as the ECG manufacturers. And also we can see the production line are getting automated a lot. So more and more SECG are are adopted or shipped to the production line all over the world. And we will have a solution for -2 86 for sure. And just so everyone know, the -2-86 standard, they are the synthesized standard to combine the three we're talking about, 25, 27, 47. They're still draft. Once they complete it, we will release the standard software for that. As far as we know, there are not much change in the hardware, so there will be no problem. Probably just one more optional standard software can solve this. Right. All right. I see no more questions coming up. So I'm very, very, into this session with you all. And this is short and sweet, and hopefully every information is easy to digest. Oh, right. Nazif. Oh, okay. I see Raphael. Yeah, to Raphael. Hey, -227 can be also covered. Yes. So you can find very similar test classes, and they can handle. And the good news, maybe you don't need MEC 2.0 for -227, because these kind of the patient monitoring ECG doesn't require algorithm. The main focus of this type of ECG category is to measure the heart rate accurately. So yeah, Raphael, -227 can be also covered by our global trio. Oh, right. Okay, thank you, Nazif. So the 62.6, so the 620K ohm is is it for different tests, okay, different tests, and C. But for the, oh wait, and the purpose is different. Yeah, CMR 51K, very likely. Yeah, so you can say stronger input impedance will actually contribute a higher CMR, and they are the different aspect of the same matters. So that actually doesn't require different sensitivity, like 12 times. Yeah. Okay. So Nazif, we can definitely talk about this more detail as we are running out of the time. And I guess we will have a next mini workshops. So if there's no new question coming up, we will be closing this session for now. So thank you everyone and hope you enjoy the first mini workshop of WhaleTeq. I'm Stefan. I'll be looking forward to see you again. See you. Have a good day.